Welcome, everyone, to today's World Resources webinar entitled Robotics Application. And we're happy that you can join us wherever you are joining from across the globe. This topic is one of much importance because robotic applications are actually shaping the future of our industry. And Industry 4.0, as you know, is now evolving into Industry 5.0. So it's a very timely workshop, and we are happy that we can be joined by the experts who are at the forefront of research on this topic. We have three presenters for today, and we ask that you keep your mics muted to avoid any distractions during the presentation. And we do have our assistant, Sandrine Williams, who will moderate the chat for us. And so if you have questions, you can put it in the chat. Or, as I am the chair of the workshop, if you raise your hand, I will allow you to speak. And I will moderate for the presenters. Each presenter has 25 minutes of presentation and 5 minutes of question and answer afterwards. So just remember to keep your video webcams closed and your mics muted to avoid distractions during the presentation. But we're happy to have your questions after each presentation. I am Debra Ferdinand James. I'm a senior lecturer at the School of Education, the University of the Westindies Mona campus, and I'm the coordinator there for the Masters in Leadership in TVET and Workforce Development, and I'm happy to be your chair. We'll have our first presenter, who is Dr. Comfort, and I'm just going to do a mic check with her. Dr. Comfort, are you hearing me? Are you hearing me clearly, Dr. Comfort?
Yes, please, I can. Yeah, I can hear you.
Okay, so I'm going to ask you, you can go ahead and upload your presentation while I introduce you. Dr. Comfort is
Okay.
a full-time lecturer at Imo State University, Nigeria. She has been there for over 2 decades, and her PhD is in computer science. She specializes in data visualization. Her research interests include Internet of Things, cybersecurity, hardware backdoors, and compiler construction. She's a regular presenter at international conferences, and she publishes widely on these research interests. Among her recent joint conference papers published in the 2022 proceedings of the International Conference on Cybersecurity, Situational Awareness, is this presentation entitled Assessing Cybersecurity Readiness of Nigeria to Industry 4.0. We're happy that Dr. Comfort can join us and share her expertise with us. And I would now turn you over to Dr. Comfort to make her presentation. You may proceed, Dr. Comfort.
Good morning from Nigeria. Sorry, as usual, we just have power outage, but I know it shouldn't stop me from going on with the presentation. My work today is on the role of robotics in STEM. Of course, by STEM, we mean science, technology, engineering, and mathematics. The role of STEM in the economic growth of any nation and recently, since 1990s, nations have actually thought it wise to bring up
robotics
different policies to get towards encouraging undergraduates to enroll in STEM disciplines. The basic goal of the STEM is to increase of STEM is to increase interest in STEM fields, to encourage collaboration among STEM professionals, to give students in STEM a better insight and understanding. At least they need to know how these fields can contribute to how they earn and the demand or the career opportunities that are bound in STEM fields. Okay, so in the science or in the science flavor of STEM, we have physical and natural sciences. We have the biochemistry is here, environmental science, hydrology, geoscience, and medicine. And then in technology, we have computer science, we have industrial design, information technology, and so many other fields now under technology. And then in the engineering we have the aerospace engineering, biomedical, electrical electronics, metallurgical, and so on. So many of the engineering areas fall under this. And then we have the mathematics, both applied mathematics, data science, and then statistics all fall within the mathematics part of STEM. Okay, and to categorize this, I have broken them down into two parts. We have factors that influence either undergraduates or interest in STEM disciplines. And some of these factors are the ability of one to actually qualify for the STEM disciplines. We know that STEM actually, whether it's technology or mathematics or sciences, there are basic subjects that are necessary for you to actually pursue any field, any career in STEM disciplines. So, and for anyone not to know maths, you don't understand mathematics, no matter how it's taught, then I don't think you're good to be in this field. So we have qualification is one of the things that provoke interest in the STEM field. We have interest and motivation from parents. We have extracurricular activities that maybe the teachers can engage in, such as excursions, such as robotic competitions, especially for children, let's say in the KG level, primary schools, secondary schools, that's the way we call it in Nigeria. And then before you get to the tertiary, which is the higher institutions, if the students at the lower level of their education have been introduced to fun activities, both extracurricular activities, in class and out of class activities that makes them make them develop interest in the things or the core courses or core subjects that make up STEM, definitely they would want to pursue a career in STEM field. Now, also observing social influences such as close friends, family members, and so on. Also, we have role models and maybe people you meet on social media and you really want to be like them. I've seen Bill Gates, he's a millionaire and a billionaire, he has money, I want to be like him. I've seen this person or that person. So there are influences like that that can actually motivate students in coming into STEM fields. So robotics, like STEM, is also a multidisciplinary field that encompasses science, technology, engineering, and mathematics. And in robotics, we have the design part, we have the manufacturing, we have the operations. Now, under the design part, we have science and technology. Under manufacturing, maybe you're talking about the arm or the different parts that make up a robot. Now we have the engineering also, technology also, and then we have the engineering part here. Then under the operations, we can talk about the programming where maybe technology comes in also, and then the mathematics. So I will talk about algorithms that make up a program. So looking at the robotics again, generally it's kind of related to what STEM consists of. So my job today is actually to emphasize on the role introducing students to robotics early in their education can play in their coming for STEM or having interest in STEM disciplines. So I've actually explained how the content of robotics, and now in the design aspects, the construction aspect, the computation and programming aspects of the robots, there is no age limit, and there is also no, let's say, young age to learning robotics. Of course, we've seen children in primary schools doing a lot with robots. And then I think with that, it will be difficult for them to deviate from or to avoid going into STEM disciplines. Now, with the robotic programming or engineering, we have the problem-solving skills. It also involves cognitive abilities. It also involves critical thinking and a lot of hands-on. Okay. Now, there is an algorithm that actually plays a lot of roles in perfectly programming a robot. When we talk about precision and the smoothness, like in animation, we look at the number of frames per second. In a smooth animation, we talk about number of frames as 24 frames in 1 second as delivering a smooth effects, visual effects. Okay, so in robotics also, we have the proportion and then the integral part and then the derivatives. And this together, we call it the PID controller. So each of the proportional controller, the integral controller, and the derivative controller plays a lot of role, that's a great role in kind of delivering a smooth move of the robot. And let's say in robots, talk about precision, talk about embedding intelligence or that can be likened to human intelligence into a robot. Now, there's no way a robot can be moving and jerky and wobbling, and then it won't be considered a perfect robot. So the algorithm PID is actually used to deliver a smooth effect, reduce the error, and then kind of get ensure precision. It can also help in predicting future behavior of the robot. So this is where I'm going to be dwelling my presentation on. So permit me, I have some tools I used for this work. Some of the terminologies you'll be hearing me say here is error, and this is a measurement of how far a robot is from its intended position. We've heard about self-driving cars. It is this same algorithm that can be used in self-driving cars because it measures the distance of where the let's say the car is moving to, let's say a stop sign somewhere, maybe 2-3 kilometers away. So it takes record of the distance and then names that as error. And then it also takes record of the present location or the status of the vehicle itself. And then between the present location and the intended position of the vehicle, it measures that as error. So what happens here is that the proportion or the size of the correction is proportional to the size of the error. That means if the distance is 50 km to where the vehicle wants to move to, the speed is given at 50 kilometers. So the closer it draws to its destination, as the speed keeps reducing, let's say it gets to 25 kilometers to its intended target, then the speed goes to 25 until it gets maybe 0 kilometers, the speed also gets to zero. That's where you now have the car stop just before where it intends to arrive at. Okay, that's for proportion. Then we have the second part, which is integral parts of the controller, the PID controller. Now, the integral parts kind of sums up all errors that the robot encounters during its runtime. And then if this it uses this summary or this integration to kind of understand whether the robot, let me use I'm using robot this time, if the robot is actually tending towards a positive, and then that becomes a trend. Once it uses that trend, it can now determine, okay, since it's going towards the positive, it is possible next time it will go towards the positive. So any decision being made can be made towards the negative direction, so that if it deviates from its track, the negative decision can bring it back to track. So this is just how it works. And then a constant value called KI is used here to tweak and tune the robot, like give it, let's say, a constant value of 2, constant value of 3, keep testing it until you get the perfect, precise tuning that will deliver a smooth effect. Thank you. So on the third part now is the derivative part. Now the derivative part has to do with taking in the present error, and then taking also measuring that together with the immediate past error. These two errors put together is now used to compare with the last measured error. So let's say I measured my error like 3 hours ago. Now I'm taking in my status, taking in the immediate, that's the error of my present. Like, remember that error is considered the distance away from the target or the targeted position. So let's say I'm in 0 and I'm going to the next 25 kilometers. So my error becomes 25 meters, like that. So I keep tweaking and checking it until I'm able to achieve my result. So in derivative, you're looking at the immediate past error and the present error. So these two combined will be used to compare to the last measured error. Now, the intention is to make predictions. So this actually is not intended to correct the move, but its intention is to make predictions. Like when we talk about machine learning, intelligent systems learn from previous activities. So this is more like the robots learning from previous errors that it has encountered, immediate past and present error being used to compare to the result of a previously measured error. And then with that, decision can be made. Okay, since it moves to the right, possibly next time it can move to the right. So I should decide that at this point, when it goes 10 kilometers, I should actually program the robot to start moving towards the left. So it's like a feedback loop that is used to make forecasting or make decisions for future trends. Okay. Now, our role here is that we kind of advocate that younger children should be exposed early. We have robotic applications that you don't have to buy robots. Like the one I'm using now is a virtual robotic environment for programming these without having to spend the money. Like I checked the price of the toolkits, robotic toolkits, and in my Nigerian currency is about 655,000. Like that's a whole lot. So, but with a virtual environment, you still have access to all the actuators and all the robotic parts that the physical robots have. And then you're provided with previous competitions. You can test and tweak you have another program software, a software called Lego Mindstorm, which is what I'm using to write the program. And then I'm testing them in a virtual environment. That's the virtual robotic toolkit, yes. So I think we can bring this as part of the curriculum for primary schools, secondary schools, so that we can bring back the mind, instead of, I've seen so many children, students in the lower class, before they are higher institutions, you ask them, they're not interested in STEM, it's difficult, it's that. So, but I believe that the maths you see me carry out here will be of a lot of interest. The physics also, where the sensors will actually be able to sense light, sense color, sense sound. I think it's so interesting that the younger ones will find that um, something to engage with. And at last, I believe they will all be motivated to make choices in the STEM field. Okay, this is my environment, but I don't know, instead of taking all day, let me just run my demo, and then maybe I'll come back and summarize. Mm-hmm. 1 minute, let me run my demo. Okay, hello, can you see my screen now? Hello,
Yes, we
ma'am.
can. Yes, we
Okay.
can.
Yes.
All right,
Yes.
ma'am. So this is the Lego Mindstorm programming environment, EV3 programming environment, and this is what I'm using to run my program. And maybe for want of time, I don't have all the, I'll just explain what I have here. Actually, if you look at my mouse, follow the mouse, you see where I have the green button there. Clicking on that is for action. Action means a function. In programming, you want to execute a task, you use a function. So in this programming environment, we have for medium motor, we have basically what we use here is for the steering. So the steering actually is to move the robots into a particular direction. So after the play button I have here, I'm using the steering component to initialize the movement of my robot. So in this case now, I'm giving it a tune of, please start at 0. Now in this environment, 0 means at a basic position, like you're not moving, you're at 0. So it starts counting from 0 to 100. That's if I want to count it in percentage. 100% is a full turn. Now, if I want to count in degrees, I can start from 0 degrees. And once I click on degrees, what I will have here is 360 degrees. That will be instead of 100. So the initial one is 0. And at that point, my arrow is straight. That means at 0, you can move just straight. Then the speed of my robot is put at 50, that's the speed. And then 0.3 is, I want you to just move a little bit using this particular component. Don't move so far, just move 0.3, maybe that's in meters or less than, that's just the distance I want you to move, and then stop. So I'm saying, use this distance, move a little bit into the line, and then stop. That's what I said here. Then a loop is used. Now, we know that robots are all about repetitive tasks. They are used where maybe tasks are repetition of tasks is highly required, and we already have definition of the task that must be done. So if you write the program and then use a loop to repeat as you like, and then the robot is now embedded with this program, the robot can actually learn from it and then be able to repeat such tasks. So a loop is used here. And then to get the loop, we have, the first one, remember, is for action. So I use the first one because I needed the steering to move. So that's a function. Now the second one is for my flow control. Under the flow control, I have the first big block there is a loop, while the second one is a switch. So the switch has its own functions. You see when I apply the switch. So now the loop comes first, and every other thing that will happen in the robot programming will happen inside the loop, so that all the programs all the activities, all the functions can be repeated as frequently as I need it to be. So immediately after the loop, the next thing I have is a switch. Now I can use the switch to test, like conditional testing, and say if the sense of light, sorry, let me show you this. Once you bring this the switch, I'm clicking here, you can see my sensors. All inside the switch, I have brick buttons, I have color sensor, I have infrared sensor, I have the motor rotation, the timer, the touch sensor, messaging, text, logic, and numeric, and so on. All these, we have them inside the switch. So right now, what I need, because the program I'm trying to execute here is for the robot to determine a path. I want it to follow a particular route, and the line on that route is marked in black. So I'm going to use a sensor and then ask that to the robot and then give it the color range that it must see. And also, let's go ahead. Now I'm adding the color sensor and I'm telling the sensor to compare two backgrounds. One is the black line where I want the robot to move and not deviate from that black line. The surrounding environment around the black line is in gold color. So I'm telling these robots, please compare two environments for me. And then what do you use to compare? Reflected light density. So if it's on the black, the reflection of the light will not be much. Now, as the reflection increases, remember this is physics now we are talking. So you see where math comes in. Okay, so now if the reflection increases, that means the robot should sense that it is going off track. So I'm telling it, I'm using a color sensor, I'm not measuring. There are cases where you just need to measure the color and that's all. But in this case, I'm trying to compare the track where the robot is right now, which is a black line, and then with the immediate surroundings around it. And then I'm telling it, compare your present color to any reflected lights that comes in. So if the light comes in, now, if the light that comes in is above 50, that's if the luminosity is above 50, please take decisions, do this or do that. Now, I'm telling it, if you look at my 50 here, immediately after the less than, I'm saying if the light intensity is less than 50, so looking on top up the like on top of this 50, you see that if I increase the 50, it's tending towards brightness or it's tending towards darkness. That means if it is less than, it is brighter. If it is greater than 50, it is darker. And don't forget, I am on the black line and I want it to remain dark. Okay. So if
Okay,
it is
Dr.
dark,
Comfort, you have 2 more minutes.
okay, well, I'll try and tidy up. All right. Okay, so right now, based on this condition, I have actions inside the loop also. So what I'm having now is if it is less than 50, sorry. Okay, if it is less than 50, I gave it a number, please come back to the line. That means I gave it a minus 51. That means do a negative turn to return back to track. But if it is greater than 50, oh, do a positive turn. So you see my arrow, initial at 0, I have a straight arrow. Then now I'm taking decision based on a condition. Now it's either it's going negative to the left or positive to the right. So permit me now to run this program, I think, and then summarize, please. I need like 5 or 4 more minutes to finish. Help me. Thank you.
Okay, I'll give you 3 more minutes.
Thank you so much.
You're
Okay,
welcome.
so let me run this program. Now, the next thing to do after running the program is to embed the program into my robot. So to embed that program into my robot, I have here the right there, bottom right of my screen, you see where we have clean up robot. That's the name of the robot that is being used right now. So I'll simply click on it and then go to the environments where I should run this. I can click on the start button here. once I say click on the arrow, it says download, and then you hear the noise. So I'm going to play this program. Okay. So I'll stop this share so I can now open the virtual environment to view the outputs. Okay. So yeah, this is my virtual environment, and it's up already. So I would want to stop the initial play. Sorry, 1 minute. My screen is covered with okay. Sorry, 1 minute. The screen is on. Okay, let me just stop share and fix this so that 1 minute, please. Okay.
Okay, you could tell us what the
I'm done,
animation
my
should
1
look
minute.
like.
Okay, it is on.
You can tell us what you want the animation to
Okay,
do.
sorry. Let me, no, it's back now. It was covered initially. Okay. Okay, can you see my screen now? So
Yeah, we're
presently
seeing
it
it. It's
is
coming up.
my robot is okay, thanks. All right, my robot is on the green carpet, and I intend for it to follow this track, the black line, to its destination. So all I need to do is now to activate it right here because I've embedded the program in it already. So
And this would be for a repetitive task where it can transport something.
okay. So it's now it's even though it wobbles a little because I've not implemented the PID, but this is how it works. Okay. And the wobbling is not much, but with the PID, you now bring in the proportion, you bring in the integral part, and then you bring in the derivative. And with that, it won't wobble. It gets the target or the challenger is to get the red carpet and then stop. Keep following the line, don't deviate from the line. Now, without this program, initial one, okay, you see that it goes off. So now implementing, yes, implementing the PID is for precision. It helps you to take decisions. It helps you to make predictions for future movements. So please, let me simply quickly go to my PowerPoint and show the view of the PID.
And there was a question in the chat asking for you to explain how the PID relates to robotics. So you can do that.
Yes, I'm going to do that right away.
Yeah.
Immediately.
So the person who
Okay.
asked that question,
Now,
I hope you're listening.
okay. Now, this is how the PID works. Like I mentioned earlier, it has 3 stages. The first stage is to measure the proportion of where the distance and then name that as error. So it's assumed your present position is okay, it's 0, but wherever you're going is an error. So with that error, it's kind of creates a trend for the robot to follow. So, and it's able to now determine the distance. Let's say I called my error. I'm going to a place that is 20 kilometers away from where I am presently. I'm the robot. And then I call my error 25 kilometers. So what happens, I set the robot to move at the speed of 25 kilometers per hour. So, and the closer it gets to the destination, it keep reducing. If it gets to 20 kilometers per hour, that's if my error is 20 kilometers per hour, the speed reduces to 20 kilometers per hour. If my error is 5 kilometers per hour, speed of the vehicle gets to 5 kilometers per hour. Now, if it gets to, it keeps slowing down. The speed, the higher the speed, that's the car moves faster. Then if it gets to my distance to my destination is let's say 5 meters per hour, eh, 5 meters, sorry, the speed of the vehicle gets very slow again until it gradually comes to a point zero where the vehicle stops. So this is actually the logic behind the self-driving cars. Now, that's for proportion. Now, I mentioned that the second part, because this proportion is actually not smooth, it just determines your error and uses that to calculate. So sometimes there's a wobble, there is not a smooth move. Now, that's where the integral part comes in. In the figure I have here, you see how the sensor, initially the sensor begins, and then my current position is taken and is written like whatever the sensor has is like zero position. So I feed that into the current position. The robot receives that zero position at its current position. So if the robot, you can write to the robot and you can read from it. So from the sensor, you write to the robot, and like we call that the current position. Now, the next one following it is the same current position, but in this case, we are reading from that current position. So we use math here to kind of tweak our system. What we have here is the threshold. We are giving it a threshold of maybe 35, maybe 40. So your job is to keep tuning your robot until you receive that perfect, precise move. Okay. So, and you have a threshold, which is, we can call it a magic number or a threshold, because we know the distance where we are going, and we know the error it's been measured. So, and we know our current location. So we are using these three variables to determine how the robot moves. So this is
Okay.
where proportion comes
So,
in.
yeah,
Now, in the
we
integral
need
part,
to
I
wrap
already
up now,
mentioned, yes,
Dr. Comfort. If you could
1 minute
wrap,
more,
yes,
please.
yes, please. Go ahead.
Okay. In the integral section also, now after writing, like I showed you the program in Lego Mindstorm, so this is how you program, you've done the programming of the proportional parts, you add that to a program for integral parts. In this second diagram here, I have the integral parts where variables for integral, the error, present error combines with the immediate past error, and then sums up to compare a previous error. Then a constant Ki is also used to determine that. Then finally, we have the derivative parts that's also we can use. That's the third one now, that's the derivative part, which is used to forecast future trends. So thank you for having me. It's a whole lot, and it's difficult to deliver this in just this short time, but I'm happy to be here. Thank you.
Yeah, and we're so thankful for having you and sharing your expertise and giving us some insights into how we program robots. It was very interesting to hear that children should be exposed to this in STEM education. I was wondering
Mhm.
what kind of success you've had with the children and those in secondary school actually taking up and being interested in STEM and then going on to university to study engineering and STEM and so on.
Sincerely, I'm just proposing this, and I wish it could be added to the curriculum in my country at least, because I know that a lot of our students are deviating from the sciences. I'm in computing, and I know uh, it's difficult to describe the lack of interest in computer science, in technology. They just come into the department and they, with intention of seeing fascinating things, like they are excited coming in 100 level, but eventually maybe because of one or two things, they lose interest because it's not exciting for them. So I believe that hands-on, especially at the level where their children in their early age, early schooling age, will go a long way to build the interest. And we can also have the competitions. Robotic competitions are everywhere. So if we have them win prizes, in competitions, that will also be a motivating factor. Thank you.
Okay, thank you very much. Do we have any other questions for Dr. Comfort before we let her close off?
Dr. Comfort, there is a question in the chat. It says, what are the applications of this model in engineering design?
Engineering design has other simulators, and but here we can design full robots using these environments. When you talk about the robot, the actuators and all the parts of the robot, you have the sensors. You can actually build. Let's say you have a physical robot, or you can go online and see a robot you think you like you want to build something similar. You can come to this environment, find out the components or the characteristics of that robot, and sufficiently you can work in this environment to develop your own robot. The one I just used is one I downloaded, and I was able to write programs, embed programs to it, and then simulate it. You understand? So, and for engineering students can actually build their own robots virtually. If you don't have the resources to build a physical robot, at least you can build one and still program the characteristics of that physical robot and have it work. That is it.
Okay, thank you for that. There's one other question, and this person asks if it is possible for you to just explain the use of sensors in robotics.
Without sensors, there's no robotics. Let me put it that way. Like the human sensory organs, we have the eyes, we have um, if you come to robotics, we have the color sensors. What they do is to sense color. Like the one I use is a color sensor. We have the touch sensors. You understand? Like when we talk about motion detectors and all that, we have cars that if you come close to them, they beep. So these are sensors working. Okay. Now, in robotics, they are embedded with sensors for the different tasks they are meant to carry out: touch sensors, color sensors, sound sensors, and so on. So I think, let me put it simple, without sensors, there's no robots. Thank you. Robotics is
Okay.
all about sensing and then reacting to what is
Yes,
sensed.
we got that. We got that. So I'm not seeing any other comments. So thank you so much, Dr. Comfort.
Yeah.
Your presentation was much appreciated, as you can see from the chat. It's very comprehensive. Persons appreciated your answers. So I'd like to ask you to stay on and not leave us, because the
Okay.
next presentation is by Professor Tamane, but it would be a video presentation, so she would not be
Okay.
here in person to answer any questions. But I know you would be able to shed light on, any comments or questions that will be
Okay.
asked. So if you can
All
stay
right.
on. All right,
I'm
thanks.
on. All right. Thank you.
Okay, you're welcome.
Dr. James. Dr. James,
Yes, please.
there's another question in the chat. The person is asking Dr. Comfort if she's able
Okay.
to share the download robot model. The link to the
Sorry.
download robot model.
The link to the
Oh, okay.
download robot model.
I'll send it. Yeah.
Yeah,
Okay,
so
thank
she would.
you.
Yeah.
Yeah,
Okay.
we use two tools, and I'll send the link to those. Thank you.
Okay.
Okay.
All right. So our next presenter, who would be doing a video presentation, is at the forefront and one of the experts in the fields of robotics. I will introduce her background, and then we will look at her video presentation. So Professor Sharvari Tamane is an accomplished academician with over 26 years of extensive experience in teaching, research, and administration. She has a deep passion for education and has dedicated her career to high quality instruction and impactful research, helping to shape future professionals and innovators. Currently, she serves as the head of the University Department of Information and Communication Technology at MGM University. She leads academic programs, guides faculty, mentors students, and fosters a culture of academic excellence. Her expertise spans both functional and technical domains, including leadership, curriculum development, big data analytics, cloud computing, and advanced database management. Dr. Tamane is committed to creating engaging, challenging learning environments that equip students for successful careers in a rapidly evolving technological landscape. As a strategic thinker and collaborative leader, she builds valuable partnerships with academia and industry alike. She is an award winning professional, having received honors such as the Best Head of Department of the Year at the CSI Tech Next India 2019 Awards. Her edited book, Big Data Analytics for Smart and Connected Cities, was recognized among the best big data books by the Book Authority. She has guided multiple PhD students, published over 95 research papers, and secured patents in innovative areas like cloud security and deep learning. Her technical proficiency spans platforms and program languages, including Linux, Python, and Oracle databases. Driven by a mission to provide students with meaningful, skill driven education, Dr. Tamane exemplifies academic leadership in preparing the next generation of experts in the fields of cloud computing, security, and big data. Her video presentation is entitled Introduction to Robotics, Components, Applications, and the Road Ahead. And I will now share her presentation.
Good afternoon, everyone. First and foremost, I would like to express my sincere gratitude to the organizers of this event, the World Resources Webinars team, for giving me the opportunity to speak on a topic that I believe is shaping the future of technology, that is robotic applications. Um, in today's session, we'll explore introduction to robotics, components, applications, and the road ahead. I'll be taking you through the key components that make up the robots, the incredible range of applications where robotics is transforming industries, and what the future holds for this rapidly advancing field. At its core, as all of you know that a robot can be defined as as a machine, so either real or imagined, that is controlled by a computer and often designed to resemble a human or animal in its movements and behavior. So these machines are equipped with sensors, actuators, and software that allow them to perform tasks autonomously or semi-autonomously. So before we see details about this topic, it's important to understand the foundational principles that guide the behavior of robots. And these are famously known as three laws of the robotics, which are formulated by the science fiction writer Isaac Asimov. Um, as you might know about, these laws are designed to govern the behavior of robots and ensure their interaction, um, their inaction rather, allow a human being to come to harm. So this law ensures that robots are designed with human safety as the foremost priority. The second law is a robot must obey the orders given it by human beings, except where such orders would conflict with the first law. This law mandates that robots must follow human instructions, provided
Dr.
those
James, sorry to
orders
interrupt, but
do
can you
not
expand the
cause
screen?
harm to humans directly or indirectly. And the third law is a robot must protect its own existence as long as such protection does not conflict with the first or second law. So, this law gives robots the directive to preserve themselves, but only after considering the safety of humans and
James,
the
please expand
importance
the
of
screen.
obeying human commands.
Okay. I tried to do that and I lost the video.
Okay.
Just one second. I will start it again. Let's see here. Okay, I'll start the video again.
Applications and the road ahead. I'll be taking you through understand the foundational the orders given it by human beings, except where such orders would conflict with the first law. This law mandates that robots must follow human instructions, provided those orders do not cause harm to humans directly or indirectly. And the third law is a robot must protect its own existence as long as such protection does not conflict with the first or second law. So, this law gives robots the directive to preserve themselves, but only after considering the safety of humans and the importance of obeying human commands. The zeroth law, it came later. A robot may not harm humanity or by inaction allow the humanity to come to harm. Asimov added this overarching law to prioritize the safety of humanity as a whole, even after individual humans. So, this is about all the laws of the robots. So, let's see the core components that form the foundation of any robot. So, no matter what is the complexity or purpose of preparing a robot, every robot is built from few essential elements that enable it to operate efficiently. So, in that, the first part is sensors. So, these allow robots to gather information about their surroundings, such as cameras for vision, touch sensors, or ultrasonic sensors for distance measurement. Actuators. So these components facilitate movements and manipulation, typically through motors or hydraulic systems. Control systems, often referred to as the robot's brain. So this part processes input and makes decisions using programmed algorithms, typically run by a computer. Power supply. This provides the necessary energy for the robot to function. whether through batteries, solar panels, or other sources. End effectors. These are the tools or devices attached to the robot, like grippers, welding torches, or drills, which enable the robot to interact with the environment. So this is about the different components of the robots which are essential to create any robot. Next is the degrees of freedom, DOF. So
Dr. James,
DOF of a robot arm refer to the number of independent movements or joints it can control. Each DOF corresponds to a distinct motion or rotation in a specific direction, and the common degrees of freedom in a robot arm are the base rotation, which allows the entire arm to rotate left or right around its vertical axis, enabling broad directional changes. The shoulder pitch, which controls the up and down motion of the shoulder joint, similar to how a human arm rises or a shoulder. The elbow pitch bends the arm at the elbow, allowing it to move closer to or farther from the body. Then the wrist pitch, which provides up and down movement, aiding the precise positioning, and the wrist yaw, which adds left and right rotation of the wrist, letting the hand or tool twist horizontally. And lastly, the wrist roll, that is the rotation, which allows for rotation around the forearm axis, akin to twisting a doorknob, giving the end effector or tool the ability to rotate for enhanced control. There are different types of robots available, which comes in different forms and functionalities. Each are designed to serve specific purposes across multiple domains. We'll see about first the industrial robots. Industrial robots are automated machines used primarily in manufacturing environments. They are designed to carry out respective tasks with high precision, speed, and reliability. And the common applications of this are welding, painting, and assembly. The robot
Okay, that is as much as I have for the video. Apparently, the rest of it is not. It's not recorded. So, do you have any questions on what was presented by Dr. Tamane? I think she sort of reinforced what Dr. Comfort shared, but if you have any questions, I'm sure Dr. Comfort would be able to shed light on that. Dr. Comfort, are you still there?
Yes, ma'am, I'm here. Yes.
Okay. Do you want to just share a little on what Dr. Tamane shared, and maybe highlight the fact that we have a female panelist, a panel of experts this time around, and maybe just highlight the trend of more women going into robotics and STEM,
Oh,
because
okay.
previously it was really a male
Yeah,
dominated field.
yes,
Yeah.
yes, that's true. Actually, we have bodies that kind of encourage women with grants, with um opportunities in the education field, with research grants, free PhDs, especially in the STEM, and a lot of job opportunities. And I think that has really paid off. We have women organizations also supporting women in developing countries, especially doing their own. And I think it has really, really paid off. Women in ICT, conferences where you see the women register free. Such things play a lot of roles in encouraging the women to come out. And they are out this time. In my institution, I have presently as the HOD of the Department of Computer Science, I have over 20 something PhD students. And guess what? Over 60% of them are women. So I think we are out and we are ready. Another thing in this line is that women have more interest in, let's say, medical fields. Ah, For technology, I give it to the men. Like in my class of computer science, in a class of, let's say, 150 students, you get to see like 30 women and we are still not there yet. So we are trying, but we've not arrived. So technological fields, you see, is still male dominated. But we have things encouraging women to come out. And in the past, let's say in my country, education for girls was quite rare. They'll tell you, you're for your husband's house. But now I think we are wiser. Men help out, married women are sponsored by their hobbies and all that. So technology is for people that are kind of subtle. And I think women are coming into it. They are less afraid of technology. We need to have what we call technophobia. I have a journal I wrote on technophobia, and that was gender technophobia. More of women being afraid of technology. But I think also that this advent of um, less expensive communication devices have also made bold the people. You have access to phones. In the past, you see women being afraid of computers, but now you carry them around. So I think that fear has really, really, really reduced. So they are coming out, and I believe in the near future we'll do better. Thank
Okay,
you.
so that's very, very encouraging to know. And thanks for sharing that. We have one question from Peter in the chat.
Okay.
Peter asks, what are the processes involved in designing and producing a robot, especially as a beginner? Well, I know that you can't answer that in just, one
Well, I can
sentence,
help.
but
Um,
you could give him an overview of what
Yes,
he wants.
yes.
Yes.
What he needs to do is to start playing, like the applications I used. You see challenges, you see competitions, so such things. You see the programs developed by others. You learn from it. They give you the insight. They give you the know-how, the hands-on, and then I don't advise a learner or a beginner to go buy robots or to go buy the parts and start building. The virtual applications are there and they do a lot. So by the time you try your hands, you're able to tune, tweak, and then program your robots, design your own robots, download it, and write programs to it. I think before you do that for 1 year, 2 years, you'll be ready to get into the real thing. Thank you.
Okay. Thank you very much. Any other questions on Dr. Tamane's short video? Dr. Comfort will certainly help, to shed light on your comments and questions. Sandrine, any other questions or comments?
No, Doc. My comment is it is really enlightening. I just wish we had more.
Okay. All right. Okay. So thank you again, Dr. Comfort, for giving us that
You're,
support there
yeah,
in responding to comments and questions. So we
yeah,
have the
thank
last presenter,
you.
and I will introduce her via her bio, and then we look at her video presentation. She is on the platform, but she has done a video presentation in the interest of time. So I'll play that for you now, and then you can ask your questions and comments as the presenter is on the platform. So she goes by Arthi SB, and she is attached to the World Resources webinar. She has an undergraduate degree in engineering. Her main areas of interest are in robotics and cobot applications, and she's very passionate about exploring these technologies and has a solid foundation in the fundamentals of robotics, including programming in Python and hands-on experience with robot operating systems. Her knowledge also extends to sensor integration, computer vision, and machine learning. This field excites her very much because it offers endless opportunities for continuous learning and innovation, and it inspires her to explore new ideas and push the boundaries of what's possible in robotics. Her video presentation is entitled Cobot Applications with Computer Visions, and I will share that with you now. I have to share my screen.
Cobot applications with vision systems, cobots, or collaborative robots, are designed to work safely alongside people in various industries. By adding vision systems, these robots can see their surroundings, allowing them to perform tasks like checking product quality, sorting items, and putting things together. For example, they can inspect products for defects or measure dimensions accurately. Cobots are easy to program and can adapt to different tasks, making them valuable in manufacturing, packaging, and logistics. With vision systems, they help improve efficiency and precision in many workplaces. Bolt picking. This bolt picking application is for Sundaram Fasteners, a manufacturing company specializing in bolts and fasteners. In this application, they need to pick a bolt from a cluttered bin and place it in a thread rolling machine for threading, then move it to a destination within a 4-second cycle time. We developed a solution that involves setting up a cobot, a vision system, and a customized algorithm for the pick-and-place operation of the bolt. We set up the vision system, a camera that will help the cobot identify and locate the bolts. Proper lighting is essential to reduce shadows and reflections, enhancing visibility. Then we calibrated the camera to define its intrinsic and extrinsic parameters. Similarly, we calibrated the cobot's arm to guarantee precise movement and positioning. Using deep learning-based algorithms, such as YOLO, faster RCNN, or SSD, we identify and locate the bolts within the image. These algorithms leverage neural networks trained on vast datasets to detect objects with high accuracy and efficiency. The cobot moves to the first bolt's position and engages the gripper to securely pick it up. After that, it navigates to the designated drop-off location and releases the bolt. This process continues for each clustered bolt, with adjustments made to the trajectory as needed. This comprehensive workflow enables a cobot equipped with a vision system and deep learning-based object detection algorithms to efficiently pick and place bolts. By leveraging advanced technology and structured processes, we enhance productivity and adaptability in real-world environments. As we begin, we see a table filled with various bolts. The vision system camera scans the entire table and takes a single picture of all the bolts, capturing their positions and orientations. Next, we watch as the collaborative robot, or cobot, comes into action. Using the information from that one image, the cobot quickly identifies where each bolt is located. With precision and speed, it picks up the bolts one by one, carefully grasping each one. The cobot then places each bolt into a box, ensuring they are stored safely and efficiently. This process showcases how the camera's single image allows the cobot to pick and place all the bolts in just one smooth operation. It highlights the effectiveness of combining a vision system with robotics, making assembly tasks faster and more reliable. In this part, we watch the cobot continue its work of picking and placing bolts. After putting each bolt in the box, the cobot uses a special algorithm to take a picture of the next bolt. As soon as the last bolt is placed, the cobot's camera captures a clear image of the next one. This helps the cobot see exactly where the bolt is so it can pick it up easily. The process is quick and smooth, with the cobot going straight from placing one bolt to getting ready for the next one. Each picture helps the cobot move accurately, ensuring that every bolt is handled carefully and correctly. By taking a picture of each bolt right after placing the last one, the cobot shows how smart technology can make assembly work faster and easier. Sequence analysis. This project is for Panasonic. They had an issue with mismatched boxes and the products inside them. We provided a solution using a single camera mounted on a cobot, which checks the attributes of the boxes and ensures the quality of the packing process. In this application, a camera is mounted on the cobot to enhance its functionality during the quality control process. The cobot approaches the designated box and begins by scanning 3 sides of the container, each containing important information. The first side features a label with the MRP, maximum retail price, and the model number, which the optical character recognition, OCR, system reads to verify accuracy. Next, the cobot scans the second side, which displays a barcode, using the camera to decode and validate the information. Finally, the third side is examined for a QR code, ensuring that the details encoded within are correct. The algorithm processes the data gathered from all 3 sides, cross-referencing the MRP, model number, barcode, and QR code to confirm they match the expected values. This meticulous checking process allows for immediate identification of discrepancies, ensuring that only correctly labeled boxes proceed through the production line. By integrating the camera with the cobot and employing advanced recognition algorithms, we significantly enhance the quality control measures, reducing errors and improving overall operational efficiency. This seamless interaction between the camera and the cobot exemplifies the effectiveness of combining vision systems with robotics for enhanced reliability in manufacturing. The cobot is equipped with a high-resolution camera that scans all 4 sides of the box. First, it uses optical character recognition, OCR, to read the MRP and model name label. Next, it scans the QR code for additional product information. On the third side, the camera captures the product name using OCR, ensuring accurate identification. Finally, it scans the barcode, verifying product details against a database. This efficient scanning process ensures that every box is correctly identified and verified for quality control. Box palletizing with cobot. This project is for Panasonic. They had a requirement for automation in the box palletizing process after packaging. We provided them with a solution using a cobot equipped with a vision system and a vacuum gripper for automation. In this application, a cobot with a camera mounted on top is used to pick and stack boxes efficiently. As the cobot moves to the area, the camera looks around to find the boxes that need to be picked up. With its vision system, the cobot can see the boxes and understand their size and position. Once it identifies a box, the cobot uses a vacuum gripper to pick it up. The vacuum gripper creates a strong suction to hold the box securely, preventing any damage. After lifting the box, the cobot moves to the designated spot and carefully places the box down in the right position. This automated process speeds up how boxes are handled and ensures they are stacked correctly on the pallet. The combination of the camera and the cobot, along with the vacuum gripper, shows how robotic solutions can make logistics operations faster and easier, reducing the need for manual labor in warehouses. The cobot approaches the box, guided by its advanced vision system. It quickly identifies the box's position and orientation. Using a precise algorithm, the cobot moves in and activates its vacuum gripper. With a secure grip, it lifts the box and smoothly stacks it in the designated location. This efficient process showcases the power of automation in optimizing workspace organization. Pan pick and place. This project is for Panasonic. They had a requirement for automation in a pan manufacturing unit. We provided the solution with a cobot with a vacuum end effector to pick and place the pan. In this application, a cobot equipped with a vision system is used to pick and place pans in a manufacturing unit. As the cobot approaches the work area, the vision system scans the surroundings to locate the pans that need to be moved. With its advanced camera, the cobot can accurately identify the pans and determine their size and position. Once a pan is selected, the cobot uses a vacuum gripper to lift it. The vacuum gripper securely holds the pan in place, ensuring it doesn't slip or get damaged. After picking up the pan, the cobot navigates to the designated location and carefully places the pan where it is needed. This automated process helps improve efficiency in the manufacturing unit by speeding up the handling of pans. The combination of the vision system and the cobot, along with the vacuum gripper, demonstrates how robotic technology can streamline operations, making tasks easier and reducing the need for manual labor. In this demonstration, we see a cobot equipped with a vacuum gripper. The process begins as the cobot identifies the pan on the surface. It carefully positions itself above the pan, ensuring optimal alignment. Next, the vacuum gripper activates, securely lifting the pan with precision. The cobot then moves smoothly to the designated location, navigating its path with confidence. As it approaches, the gripper gently releases the pan, placing it exactly where needed. This efficient pick-and-place operation highlights the capabilities of collaborative robots in automating tasks with accuracy and ease.
Okay, I hope you enjoyed Arti's presentation. Arti, are you there?
I'm here.
Okay. Now, do we have any questions for Arti?
There are currently no questions in the chat.
All right. Uh, could you go ahead and post the link for the attendance, please, Sandrine?
Sure, Doc.
Yeah. Now, just remember to fill in the information in the attendance link with the name you want on your participation certificate, so that we don't have to redo it, and the spelling is correct and everything. Okay. So, RT, could you give us a little more insight into how you were able to attract those projects and deliver what was needed to solve the problems?
Yeah, we implement this project uh, for replacing a monotonous work, and we implemented deep learning to detect the objects. Mm, we implement deep learning and we implement a camera.
Okay. And you have an engineering background. So
Yeah,
if someone wanted to venture into projects like this, what would be entry level experience and qualifications to get involved in these exciting real life projects?
the knowledge of deep learning and machine learning, and
Okay.
able to write a code by using Python.
Okay. So it's not too demanding in terms of gaining entry into the field, to be able to start working on projects. Did you all experience any challenges, like in a pilot test, and when you did your first round of testing, did everything just come together, or you had you know hiccups and challenges, and how did you deal with those?
Yeah, we did many mistakes, and by the mistake we learned many things. It took
Okay.
time to learn these things.
Okay, so what time frame you're looking at? How long did it take you?
If we are interested and we are into this with full interest, we can learn within 1 or 2 months.
Okay, okay. That's not too long. All right. So that was very exciting and very interesting to see the application of the cobot. Um, how would you describe your experience, as working along with the robot, which is a cobot? How would you describe that experience working alongside a robot?
It's quite interesting working with the cobot. We have a collaborative robot.
Okay, so
Uh,
do you feel like
uh,
it's almost like a partner you have there, or it's just like you're interacting with a machine?
Sorry,
The interaction with the cobot, do you feel it's just another machine you're working with, or it's more than that? It becomes like a friend or a
it's like
person.
a friend to us because the collaborative robot, it's able to work with a human.
Okay, so that's interesting. All right, do we have any comments or questions for Arti before we close off?
No,
All right, Sandrine, anything in the chat?
No, that there is nothing in the chat except for earlier. Persons were asking Dr. Comfort to please send the link for the robot download application.
Okay, so Dr. Comfort, are you there? Okay, I'm not sure if she's hearing me. Okay, I am not seeing her on the platform. So, what we'll do, we will, Sandrine, please send
Yes,
her
sir.
WhatsApp. Yeah, please send her WhatsApp so that she
All right,
can,
I will.
yeah, she can send us the link. And what we'll do, we'll send it to you via email, just as how we sent out the invitation for registration. We will send it. Oh, I'm seeing something here. Oh no, that's the attendance. Okay. All right. So we'd like to thank you very much for your attendance and participation, your questions, comments. It's all very encouraging so that we can offer more webinars that are of interest to you and to help you keep abreast of the application of robotics as the field evolves and advances. We can help you to keep abreast of what these changes are. We'd like to thank our esteemed panel of experts for their presentations and appreciate the fact that they took the time to do the video presentations as some of them were not able to be here with us. They already had other commitments that they had made, and so we thank them for that. And we'll also like to thank Dr. Krishnan and also our new assistant, Sandrine, for all the coordination behind the scenes, getting things ready so that we can have a successful webinar once again. So we'll close off here. Do remember to fill in the attendance link and enjoy the rest of the day and the weekend, wherever you are in around the globe. Thank you very much.